Alright, I've had some questions from people about how to get started on the code for this next lab, the pulse width modulation, lab 5. Couple of suggestions. First suggestion is, start small. Start off by just making something that does your fixed waveform. And this is 256 milliseconds for each pulse. And this doesn't change duty cycle. This is the waveform that's just coming out at the constant frequency. And how do we do that? Well, one option is imagine we have a 1 millisecond interrupt. What should we do in that code? Increment a counter, and then see if that counter is equal to 0. And if it is, toggle the output. And then return from your interrupt. Alright, so what does this do? Every millisecond we get an interrupt, we increment a counter. Our counter is an 8-bit number. It will overflow after 256 increments, which means it will reset to a value of 0. After 256 increments, that means we've gotten 256 interrupts. That's 256 milliseconds. So when the counter reaches 0, we toggle the output. The counter is now 0. It'll take another 256 interrupts, 256 milliseconds, before the counter reaches 0 again, and at that point we toggle the output and the output goes high. So this is an interrupt driven approach to generating that basic waveform, right? Just wait for 256 events and toggle your output. And then if we want to also deal with this business of the duty cycle, what we can do here is say if output is low, adjust the duty cycle. So we have a separate waveform being generated at a much higher frequency, but it can have a varying duty cycle. And basically we want to change that duty cycle every half second. Well, that can happen at each of these points where this slow moving waveform has changed from high to low. So this part of my algorithm will toggle it every quarter second, and by adding in a little check here after we toggle the output, see if the output has gone low, well, that will happen every half second. And at that point we can update the duty cycle. Alright, so the other question I'm getting is how do we update the duty cycle, because we're not using the PWM subsystem. So let's suppose we want to generate a 25% duty cycle. So let me just write you some pseudocode here, a flowchart, just for generating a 25% duty cycle. Forget about everything else, right? What do we have to do? Set up interrupts for 1 millisecond. Okay, that's part of our initialization. Set, I don't know, I'm just going to call this fast count equal to 0. And then loop. Okay, this is not going to be part of your final code. This is just looking at, hey, my whole purpose in life is to generate a waveform with a 25% duty cycle using interrupts. How can I do that? Okay, I'm going to set up my 1 millisecond interrupt interval. I'm going to initialize a variable fast count to be 0, and I'm just going to sit here and spin. Alright, so when I get my 1 millisecond interrupt, what do I do? Oh, the other thing I'm going to do here is set my output to 1. Okay, so when I get an interrupt, what am I going to do? I'm going to say fast count equals fast count plus 1. And then I'm going to say, is fast count equal to 1? And if it is, I'm going to set my output to be low. And then I'm going to say, is fast count equal to 4? And if it is, I'm going to set output equal to 1, and I'm going to set fast count equal to 0. And then I'm going to retfee. Alright, what does this little chunk of code do, right? So fast count's initialized to 0. When I get an interrupt, it's going to increment it to 1. It's going to say it's equal to 1. It's going to pull my output low. And fast count's not 4, so I'm going to return. The next interrupt, fast count's going to be 2, no, no, return. Next interrupt, fast count's going to be 3, no, no, return. The next interrupt, fast count's going to be 4. It's not equal to 1, but it is equal to 4, so my output will go high, and fast count resets to 0. So what does this do? Let's look at our output. Let's look at fast count. And let's look at time. Okay, so I'm going to mark off time in milliseconds. So here's 0, 1, 2, 3, 4, 5, 6, 7, 8. Alright, we initialize fast count to 0. We initialize our output to be 1. Alright, first interrupt we get, we're going to increment fast count. So fast count's going to become 1. And if fast count is 1, what do? We set the output low. And then fast count's not 4, so we go back. Okay, so our output's low. 2 milliseconds in, we get another interrupt. We increment fast count to 2. It's not 1, it's not 4, we don't do anything. Millisecond later, increment fast count to 3. It's not 1, it's not 4, we don't do anything. Millisecond later, we increment fast count to 4. It's not equal to 1, but it is equal to 4. So what do? We set the output high, and we reset fast count to 0. And we're right back to where we started. A millisecond later, fast count will be 1. It's equal to 1, so we set the output low. And then a millisecond later, we set it to 2, and then 3, and then we set it to 4, and at 4, we'll set the output to be high, and we'll reset fast count to 0. So this flowchart, right, relatively few statements, will generate an output with a 25% duty cycle. And all we've got to do is we got to have this counter, which is counting, how fast we are and how far we are in this fast-moving pattern. If it's equal to 1, drop the output. If it's equal to 4, raise the output and reset the counter. And then if we decide that we wanted a 50% duty cycle, what has to change? Just change this 1 to a 2. And if you want a 75% duty cycle, change that to a 3. So this is just an algorithm for generating something with this fast 250 Hertz frequency and with a variable duty cycle from 25 to 75%. So you can get this working completely independent of everything else in the lab, right? Make a separate experiment, close all your projects, start a new project, and just try to generate this 25% duty cycle with this 4 millisecond period. And then, close that project, start a new project, and just try to generate this slow-moving signal that toggles every quarter second. And then once you have those pieces working, figure out how you're going to adjust the duty cycle. And you can do that by, having a counter DC equals 0, and each time you need to adjust the duty cycle, add 1. And if the duty cycle is equal to 9, set it back to 0, or whatever that number turns out to be. And then when you adjust the duty cycle, you know, make yourself a table. If my duty cycle variable is 0, I should be at 100%. This should be 75. This should be 50. This should be 25, 0, 25, 50, and so on. And when we do this little piece of code and we say, hey, I want my waveform to be a 50% duty cycle, what do we need to do? Well, we need to change this from a 1 to a 2. How do we do that? Well, instead of hardwiring a 1 here, make a variable, you know, duty cycle magic number. And if fast count's equal to duty cycle magic number, you know, set the output low. This is always going to be a 4 because that's, you know, the frequency of the waveform. And then in here, when we want to adjust the duty cycle, update this variable, and based on that and this table, set your duty cycle magic number to, you know, 3, 2, 1, 4, 0. The edge cases are special. If you want a 100% duty cycle, don't do any of this. Just leave the output high. If you want a 0% duty cycle, don't do any of this. Just leave the output low. But if you want something in between 25, 50, 75, this is an algorithm that will take care of that for you. All right, hopefully that helps. Thanks. Bye.